This time we're going to explore key concepts regarding one of the 4 macromolecules we can find in cells. Remember that those molecules we describe as a cliche as the molecules of life are going to include carbohydrates, lipids, proteins, and nucleic acids. Let us concentrate right now on the lipids for a moment. And one of the most common forms of lipids cells are going to be using, sometimes building these kinds of molecules or sometimes breaking them down as a source of energy. Those are going to be the fats. Fats are also known as triglycerides and include 3 different types that you may be familiar with. For example, unsaturated fats are going to be those that are often known as oils. They are usually from plant origin, and they're going to be liquid at room temperature. We also have the saturated fats. These are going to include butter, lard. They can be solid or semi-solid at room temperature, and these usually are going to have an animal origin, although not necessarily. They're going to be also saturated fats that can be obtained from plants. And the third type, and these are going to be known as the hydrogenated fats. These are usually manufactured in an industrial setting. A factory will be taking what we know as unsaturated fats from plants, oils, and they're going to be transforming them for the purpose of increasing the shelf life of products we consume. For example, cookies, many kinds of baked goods. They're going to be lasting longer when they are cooked with hydrogenated fats rather than unsaturated ones. And with that also comes a set of complications, because these hydrogenated fats, as it turns out, have been linked to heart disease and to a number of other cardiovascular problems. Now, what I want to do is I want to explain to you a little more how these fats or triglycerides are going to be forming. I'm going to be using my laser pointer. I hope you can see this red dot on the screen as I move it along. Here we can see that for a triglyceride, there is going to be one key component, which is going to be a glycerol molecule. I'm moving my laser pointer around this. This glycerol molecule is going to have 3 places where fatty acid chains can be connected to. Here we see an example of a fatty acid. This is polymeric acid. And notice what happens. At the one end of polymeric acid is going to be, let me see, perhaps I can increase the magnification so you can see better on the screen. There's going to be this carboxyl group. And carboxyl groups in biology are going to be forming substances we call carboxylic acids. And for that reason, this molecule here receives the name of a fatty acid because of the carboxyl group and the carboxylic acid nature of it. Notice how this fatty acid with the carboxyl group at the one end is going to be engaging in a chemical bond with the hydroxyl portion of the glycerol molecule. And so this special type of bond that happens between this hydroxyl and the carboxyl is going to be known as an ester linkage. And we can see that new bond that has been created right here. This is going to be the ester linkage. And so in the case of fat or triglyceride, there are going to be 3 of these fatty acid chains or tails, as we may want to call them, that are attached to the glycerol molecule. And so this is an essential detail that I want you to remember, not only for the exam, but for other properties of life we're going to be studying in the future. So this glycerol is one of the components of triglyceride and the 3 fatty acid tails. Now, going back to the idea of unsaturated versus saturated, I mentioned at the beginning of this presentation. The difference is going to be with regards to how the carbons are going to be bonding with hydrogens. I want to go back to the previous illustration. I like this one because you can see in better detail how in this carbon skeleton portion of the fatty acid, carbons are going to be attaching to other carbons. I'm looking at this portion here in the middle of the molecule. I'm hoping you can see the little hand that is showing as a cursor. And so each carbon bonds to 2 carbons, but also each carbon is going to be bonding to 2 hydrogens when we're looking at this middle of the hydrocarbon skeleton. And so each carbon, in an essence, is bonding with as many hydrogens as it can while still attaching to the remaining carbons in this carbon skeleton. In that sense, because carbons are bonded to as many hydrogens as they can, we're going to be called this a saturated fatty acid. And in this illustration, you can see that all three fatty acid chains are going to be of that nature. There are only single covalent bonds between the carbons along this hydrocarbon skeleton. Now, what happens is that sometimes instead of a single covalent bond, there's going to be a double covalent bond. And when that double covalent bond forms, now carbons cannot be bonding to the maximum number of hydrogens, which, as you remember, was 2 hydrogens. Now each carbon here is going to be bonding only to 1 hydrogen. So these fatty acid tails are going to be unsaturated with regards to the numbers of hydrogens attaching to the carbons. Remember, this is an important detail. The reason carbons can only, the carbons at this location where this double covalent bond can be seen, that'll be in this representation a carbon right here, and there'll be a carbon right here, and this is a double covalent bond between them. These two carbons each can only bond to 1 hydrogen atom. And so this is the reason we call this an unsaturated fat molecule. And what you see in most unsaturated oils is going to be that at least one of those 3 fatty acid tails will be of this nature, of the unsaturated type. So there you see a side-by-side comparison of what a saturated fat looks like and the difference with regards to the unsaturated fat. From a nutritional point of view, both of these can be important forms of nutrients for our body. Even those we call saturated fats are going to provide benefits in terms of providing a lot of energy in a compact way of packaging as much energy as you can per unit of mass, per gram. So that's one of the advantages. When you think about animals that are migrating or animals that are going to be hibernating during the winter, they're going to be storing excess energy in the form of fats. And the uses and the benefits of unsaturated fats, I mean, we can develop an entire class just to talk about that. I just don't want you to develop or continue with an idea some people have that fats are bad. Not all fats are bad. In fact, many fats have positive effects on our health, in our well-being. In addition to those 3 types of fats, the hydrogenated, which are not so good, then the saturated and the unsaturated, which have beneficial properties for our diet, there are also going to be waxes. These waxes are usually going to be lipids that have a protective type of nature. We also have the steroids, which are going to help maintain the integrity of cell membranes. That is going to be the case of cholesterol. And this molecule, cholesterol, which is also vilified, sometimes presented in a negative light, actually has beneficial contributions in our bodies. Our bodies have the ability to synthesize cholesterol. And if we consume some with our diet, don't worry. There are uses for cholesterol in our bodies. And one of those uses can be seen in this illustration. You can see that testosterone, a sex hormone that not only controls sexuality, but is also going to be responsible for, to a degree, for the metabolic rates in our bodies, is going to be a derivative of cholesterol. We can use cholesterol and then from that transform it, modify it to make something like testosterone. Estrogen is going to be another type of sex hormone that is derived from reactions that modify cholesterol into this type of a sex hormone. So steroids can have beneficial roles also in our body. And then we have phospholipids. I'm going to save most of the discussion on phospholipids for when we talk about membranes, the properties of membranes, and the kinds of transport happening across the membranes of a cell. Phospholipids will be described in greater detail then at that point because they're the essential component of a plasma membrane. Here we see 2 representations of a phospholipid. One where you can see the nature of the fatty acid tails. These are going to be hydrophobics. because of the hydrogens and the carbons are bonded in such a manner that it doesn't lead to any partial charges. And so when you put fats in water, all the water molecules, they are cohesive, they attach to one another, and they exclude these nonpolar bonds that are seen between carbons and hydrogens. Notice that there are going to be different regions in a phospholipid. There's going to be this part over here where the fatty acids are. We describe this as hydrophobic tails. There's going to be only 2 of these, and that is different from a triglyceride that actually happen to have 3 of these fatty acid tails. Now, there's also going to be a region that is known as a hydrophobic head, and this hydrophobic head has a couple of components that are going to make this part of the molecule combine with water, mix with water, and that's the meaning of hydrophilic. Hydrophilic means water-loving. So water molecules can be attracted to this negative charge on this phosphate group. Here we see another example of one of those functional groups that are essential for us to know and to remember. And there's also going to be a choline. Not all not all phospholipids are the same. There's going to be a few variations of phospholipids we can find in living things. This one happens to have choline, and the reason I'm mentioning this choline, which is located at the tip of this hydrophilic head, is that there's going to be a positive charge where this nitrogen is, and so every time you have molecules in water that have partial charges, like this positive in choline and like this negative in the phosphate group, those are going to interact with water molecules, and they will be able to dissolve in water. But this portion over here is not going to be soluble in water. So what happens in a membrane, and I'm going to go to a zoom mode so I can show you better what's happening in this illustration, is that the phospholipids of a membrane are going to be oriented this way. Let's say that this is the outside of a cell with an aqueous or water-based environment. The hydrophilic heads are going to orient in the direction of water. And if this was the inside of a cell, if this was the cytosol, then the hydrophilic heads, because they welcome water, because they love water, will also be oriented in this fashion. Because it's a bilayer, we see one layer of phospholipids up on top of this illustration and another one down on the bottom. Notice how the hydrophobic tails, hydrophobic means water-fearing, hydrophobic, these parts are going to be non-polarly bonded atoms, carbons and hydrogens, and because they are not dissolving in water, they're going to be oriented to towards each other, where they do have the affinity of combining well with one another. So the hydrophilic heads are going to be oriented in the direction of water, and the hydrophobic tails are going to be tucked in the middle at the core of this phospholipid bilayer away from water. And so these are the most important details about lipids that I want you to remember. Next up will be a presentation on proteins.